unmute you now. It's being recorded,
Oh.
so you should be all good.
Cool. That's great.
Cool. Just make sure, how many of you guys are speaking? Are there gonna be 3 of us? Just make sure you pass the microphone back and forth whenever you're speaking. Yeah, you can record on your end too, but I already have it recorded.
What time is it? 1 minute left. Yeah, I think 35, right? It is recorded. It's 35. Okay, let's start. Hello, everyone. Can you hear me? For this recitation, we will briefly go through first about the Autograd and also about the homework 1 bonus, and then about how can you compute the partial derivative and all of those things about differentiations that can get familiar with the chain rule, actually. Yeah. And yeah, so that is the agenda today. First, I will introduce the homework 1 bonus Autograd and also the computation graphs. So let's start with the Autograd. So this is like a totally optional bonus homework, but I highly recommend you to at least take a look because that is something pretty new, and all of those libraries like PyTorch or TensorFlow basically use this as their like ways to compute partial derivative. And in the class, you may remember that when you compute all of those backpropagations, actually you are compute lots of intermediate values and use them to compute for the next step partial derivatives, and then use chain rules to do everything. So this is, this follows basically the same logic for that, but in this time you are not computing all of those neurons within the multilayer perceptrons, but you are compute all of those operations like plus, multiply, things like that. And in this homework, you will learn this whole framework which we call automatic differentiation that actually do these things that you are going to store all of your operations of your functions into a list and then compute them in a reverse way for each operations. You compute the derivative of that. And the key idea is that first, all those calculations are going to break down into several basic operations. And second, you're going to use a list to store all of them. But then, really important is that you are going to compute them in a reverse way. And I will go through the reason why later. And here is just an example. For example, if you have a function that is y is equal to w multiply x plus b, which you can break it down to 2 parts. The first is w multiply x, and the second is c plus b. And then you can compute them, follow this order in a reversed way. So the reason to do this is you can imagine, let's say you have a function like this, which is like to multiply all those variables together. If you are going to compute the partial derivative of to each variables, basically you are going to compute for n times n minus 1 times for some repetitive things. So if you are going to like naively compute it for your backpropagations, there are a lot of repeating things you compute within this whole process, which is the waste of the times and also your space. So based on this, there is actually another idea that is to use the computational graph to represent this whole function. And then we can compute them one by one by all of those nodes. So you can see this graph is really similar to actually how the multi-layer perceptrons connect together. You have all of those activation functions, and then you are going to compute the backpropagation for that. And also, very kind of intuitional way to do this is you can compute from the left to the right. Let's imagine that you have the x1 and x2 as your input values, and then you have y as your output values. then you are going to compute the partial derivative of the y to x1. Then you can have the partial derivative of x1 to x1 itself, which is 1, and then x2 to x1, which is 0. And then you can start all of those computing of the, let's say the v3 is actually the v1, is the ln of the v1. So basically the partial derivative of v3 to v1 is v1 partial derivative of v1 divided by v1. So by doing this, actually you can do like a forwards of all of those partial derivative computation, and finally you can get a value that is y to the x1. But in here, you also may notice that, let's say, this is the whole process of you compute the partial derivative of the 1 to x1. But then if you are going to compute the partial derivatives of the y to x2, you are going to do these things again, but just change these two values of the v1, v2 to 0 and 1, because in this time, you are doing it from the partial derivative of the x2 to x2 and then x1 to x2. So you can see still there are, like if you have multiple input variables and you are going to compute the partial derivative to all of them, you are going to do this starting process for all of those variables, and then start all of those things happening follow with this. So still, this is like lots of like repetitive computation, because you can imagine for our multi-layer perceptron or deep learning architecture, actually the n will be really large, but then the k will be something like 1. So how can we also avoid all of those repetition? There is another idea is to compute in a reversed way. So we start from the right side. Let's say now we have the y value here, and then we start to compute all of those partial derivative of the nodes in the middle. So first, we have the v7 to v7, which is 1, definitely. And then for the v7 to v6, because you can see the function will be the v6 plus v5, and which the partial derivative to the v6 will be the v6 itself, right? So it's still 1. And then v5, because, it's minus. So for the v5, it's like minus v7, so which is minus 1 here. So by doing this, actually you can have only one starting point, which is your final value, and then you can do it's really similar to backpropagations that you start to compute them one by one. And only one thing to notice is, let's say for V2, you can see for the V2, there are two branches. One is that actually the V1 time V2 to V4, which is contribute a part to the V2. And then another part is sine V2 is equal to V5. So that is another part contribute to the partial derivative of V2. So it's really like the, in your backpropagation, you are going to add these two things together. So for the computation of the partial derivative of the V2, actually that is, you are going to have the V4, the partial derivative of the V4 to the V2, and then V5 to the V2, and add them together here. So yeah, that is the overall logic, like how you compute from your ending point and gradually go through all of those backwards. And by doing this, you can see the benefits is you don't have to, let's say, start from x1 and then start from x2 and do the forward things twice, but then you can do everything in one backwards. Yeah, so that is the overall about the Autograd, and I highly recommend you to check the first link. So that is from the Tianqi's course that is just happening for this semester, and he has a very detailed description about how the automatic differentiation is working and why we are going to do this. Yeah, so that is my part. Oh, by the way, any questions?
So Zishan would be leaving right now, so if you have any questions, now is a good time. All right. moving on. So during backpropagations, you will find that we're doing pretty much the same thing. So we deal with something we know as loss. And before we continue, let's understand what loss really is. So the function we want to minimize or maximize in some cases is the objective function. Now, when we are minimizing it, we may also call it the cost function, loss function, or the error function. Now, there are two main functions of the loss. One of them is to evaluate the performance of the model and essentially lower the loss, the better the model is. And the second one is its role as part of the optimizer. Now, the backpropagation of the loss. So we can't really do backprop without having the loss, and it's really the starting point. So in backprop, we aim to minimize the cost function by adjusting a network's weights and biases, and the level of adjustment is determined by the gradients of the cost function with respect to those parameters. And we kind of knew this from before, but let's go a little deeper into it. This is a quote from the lecture. So the gradient is the transpose of the derivative. So we do want the gradient while doing the backprop, but essentially it's a transpose of the derivative, which we'll be calculating. And these are the steps for training a network. So the derivative, right? So mathematically, the derivative of a function measures the sensitivity of the change of function with respect to a change in its input value x. You can see in this graph that it's a linear function, so the derivative remains the same throughout. But this doesn't usually happen because in most cases, the function is a nonlinear one and the value changes with, at every position of x. So it looks more like this. And say we have del y. So del y changes at every position of y, right? So this is what the derivative of a nonlinear function looks like. The slope here changes at every point. And if we let y equals f of x, the function, be a relation between two variables, y and x in this case, and if the function is continuous and differentiable, any small perturbation of x will result in a small perturbation of y, and we are essentially able to see how much one affects the value of the other. So in some cases, the value del x can also be represented as del parentheses x because it's essentially a function of x. As x moves, this value also changes. All right, so moving on, we know the derivative of y with respect to x as del y, and the symbol you see in bold is nabla x of y times delta x, and the shape of the derivative for any variable will be transposed with respect to that variable. For example, if a function with a scalar, and if we have a function with scalar input x and scalar output y, its derivative would be a scalar. And for a function with dimensions d cross 1, vector input x and scalar output y, its derivative would be a row vector with dimensions 1 by d. And similarly, like if we have, let's consider another example. And if for a function with a d by 1 vector input x and a k by 1 vector input y, its derivative is a k by d matrix. Why is this important? Because when we are calculating the derivatives, if we just check the dimensions of our vector inputs and the vector outputs, we'll be able to understand if what we're doing is right or not right, and potentially like fix a bug. All right, so scalar derivatives. So in this case, we have a scalar input and a scalar output. We can see del y is represented as f prime x times delta x. And when we are dealing with multivariable derivatives, we have a vector in and a scalar out. So the difference is the input of scalar versus vector. And in the case of vector, we have delta y as represented by delta y with respect to x times delta x. And this can be represented as a matrix, which with each element being the partial derivative of y with respect to xi. So del y by del x1, x2, x3, so on and so forth. And this really captures the essence of how x, the different values of x and the different elements of that loss function makes a difference in the value of y. And we need this while calculating the gradients. All right, so let's talk about multivariable derivatives when we have vector input and vector output. It's a little different in this case because the input is 1 by d input and the output is 1 by k in this case. So k by 1 and d by 1. And if you see the k by d matrix, that essentially captures the essence of the derivatives of xi with respect to yi at every instance. And this value that you see, del y with respect to del x, the first term, the k by d matrix, is also known as the Jacobian, and this would pop up in a quiz maybe this week or in the future, so just keep that in mind. All right, so the key ideas that we learned about derivatives: the derivative is the best linear approximation of f at a point. The derivative is a linear transformation, a matrix multiplication essentially, and the derivative describes the effect of each input on the output. Any questions at this point? None? Anyone on Zoom? All right. All right, so now we'll go through computing derivatives of specific use cases, and we'll see how it's done. And later, when during the class or whenever you're trying to compute the derivatives, if you come across like a big function, you don't have to be afraid. You can always break them down into like smaller bits and apply one of these 7 or 8 methods, and you should be able to find your derivative. So let's start with the simplest use case of when we are applying the scalar chain rule. So here we have a function which computes the loss with respect to an output z, and z is a function g of x. In this case, all terms are scalar, and the derivative and the del L by del z is given by this relation. So we have del L by del z times del z by del x, and del L by del z when we multiply by g prime of x, we already have the first variable, del L by del z. So we can use that to compute the value of the derivative of L with respect to x. All right, so moving on to scalar addition, it's also similar. We have a function f, which computes the loss with respect to an output z. In this case, however, z is a sum of 2 different parts, x and y. And again, all terms are scalar, so the derivative of L with respect to z is given by del L by del z times del z by del x. And in this case, del z by del x is just an identity matrix, or like it's 1 essentially, so that cuts out and we have del L by del z. Similarly, for the second term in z, which is y, we have the derivative of loss with respect to y is del L by del z times del z by del y, and del z by del y is again 1, so we are left with del L by del z. Pretty straightforward, just takes some practice, I guess. All right, so scalar multiplication, similar, we have a function f which computes the loss from an output z, and z is represented by w times x. Here, w is a capital letter, but essentially w is also a scalar. So when we're trying to compute the derivative, so the derivative of L with respect to z, we do 2 different parts, so del L by del x and del L by del w. But if you see the order of the derivative here, like towards the right side, del L by del z times w, and the x is written before del L by del z. So the order doesn't really matter here, but it will matter when we are dealing with vectors. But essentially, because we're dealing with scalars, the order doesn't really matter. And it's again a simple partial derivative of L by z times z by x, which gives us the 2 derivatives. All right, so now we move on to the scalar generalized rule. So in this case, we have a function f, which takes an output z to compute the loss, but z has multiple elements. So we have z1, z2, like zi throughout, and every z is a function of x in a different way. So gi through gn represents the relationship x has with their respective z, and it's affecting the loss in different ways. So when we compute the derivatives, we have to capture the essence of all of those x's and how they're affecting the loss. So when we take the derivative of L with respect to x, we can see the derivative of L with respect to x is essentially the derivative of L with respect to z times del z by del x. And this term del z by del x is essentially the summation of all of the relationships of x with respect to the respective g's. So del gi by del x throughout will give us the relationship x, or like how x affects that function g. And when we take a summation of all of that and we multiply it with del L by del z, we have our derivatives. Any questions at this point? All right, also we use like the addition to represent these, to understand how all of these terms affect L, because like we don't use like say multiplication, for instance, because we don't really know how G is related to the loss function L. So we use addition to add up all of those relationships. All right, so now we move on to the multivariable chain rule. In this case, this is a little different from the scalar computing derivatives that we just talked about. In this case, the function f takes an output z, where z is a function of x. However, in this case, L is an m by 1 vector, x is a d by 1 vector, z is a k by 1 vector, and del L by a derivative of L with respect to z is given as a m cross k matrix. And you can see the math here. So we have derivative of L with respect to x equals the derivative of L with respect to z times derivative of z with respect to x. And this checking of dimensions is really important because as things get more complicated, this is what's going to help you debug your calculations. Moving on to multivariable vector addition, it's similar to the scalar method. However, we just have to take care of the dimensions again. So in this case, x, y, z are all d by 1 vectors. The derivative of L with respect to z is given as a m by d matrix. And so z is a sum of two different parts. So we take the derivative of both of them individually, and we have del z by del x and del z by del y, the second term in the center part, as 1. It's essentially an identity matrix. So that cuts out, and then we have del L by del Z as the derivative of both of those parts. And the dimensions again, M cross D matrix is the output, because there are, when we're calculating it, we multiply an M by D matrix with a D by D matrix, and we have a result. All right, so computing derivatives for multivariable vector addition of derivatives. In this case, the loss function is the sum of two different functions. So L is defined as f1 of z plus f2 of y, and z and y are both functions of x. So you can think of this as the loss coming from two different parts, and both of those parts are a function of x in a different way. So to capture all of these relationships, when we take the derivative, we keep that into account. We'll go through that in a second, but x is a d by 1 vector, z is a k by 1 vector, y is an m by 1 vector, and the derivative of L with respect to z is an n by k matrix, while the derivative of L with respect to y is given as an n by m matrix. Now, when we take the derivative of L with respect to x, we do the product of del L by z and the derivative of z with respect to x plus derivative of L with respect to y times derivative of y with respect to x. And if you can see, the dimensions all add up. N by d is n by k, k to b, yeah, it all adds up. All right, so the multivariable matrix multiplication. Again, this is similar to the scalar method. However, in this case, the order of the derivatives matters. So we'll get to that in a second, but here the loss is a function of z, where z is represented as w times x. However, here w is not scalar. It's given as a k by d matrix, and x is a d by 1 vector, z is a k by 1 vector. So the derivative of L with respect to z is given as a 1 by k vector. So if you look at the computations on the bottom, derivative of L with respect to x is a product of derivative of L with respect to z and derivative of z with respect to x. And the second part is essentially just w, and that is a 1 by d matrix, a 1 by d vector. And the derivative of L with respect to w is the derivative of L with respect to z times the derivative of z with respect to w. And in this case, the first part of it is just x, so we get a d by k matrix. Here, the order really matters. So if you see the placement of x right here, if we were to like move this after del L by del z, it's going to create problems because the dimensions wouldn't add up. This was not the same as the scalar case. All right, so computing derivatives of multivariable generalized chain rule, the generalized chain rule. So we have a function which computes the loss function after taking an output z. Z is a combination of different elements, z1, z2 through zn, and every z is a function of x in a different way. So we have gi of x for every z that we have. So the loss here is a m by 1 vector, and the x is a d by 1 vector. We already know that z is a k by 1 vector, so we get the derivative of L with respect to z as given by an m by k matrix. So you can see how we compute the derivatives of a multivariable example. So the derivative of L with respect to x is essentially derivative of L with respect to z and derivative of z multiplied by the derivative of z with respect to x. So the second part of this, not equation, but relationship is the summation of all of the products, the summation of all of the derivatives of z with respect to x. So we need to calculate how much x affects z for each of these cases, and then we add it up to get the complete derivative. All right, so that was it. So we have multiple ways to compute the derivatives for different types of functions that we have and different types of problems that we're dealing with. Now Fuyu is going to talk about a complex example. Any questions? Yeah.
So to be clear, when this is loss is L and M by 1 vector, the loss is a scalar, right? But that's the dimension.
Here the loss is a vector.
Here the loss is a vector?
Is a vector.
Okay.
So just to recap. Yeah, so we do two types of computations. One is the scalar derivatives, and then we deal with variable derivatives. So the difference in both of these situations is that in the first one, the input is scalar, and in the second one, it's a vector input. So if you look at the dimensions too, yeah, so the loss is an m by 1 vector because when we multiply that with the m by k matrix, we get the result. No, the loss is the output, so we don't multiply that. But yeah, we get that when the m by k matrix, which is then n with respect to z, is multiplied by the z with respect to x, which is a k by 1 vector. So we get m by 1 vector as the output, which is the loss.
Okay, cool. And practically, would the loss ever be a vector?
Yeah, it would never be a two-dimensional matrix.
Because isn't the loss what we're trying to minimize? And like, are we trying to minimize one number?
Not really. The loss would, at least in this course, will almost always be a vector.
Like cross entropy loss? Doesn't that return like a? Oh, because it's the loss for each one, and then you take the average of that, right, for each data point.
Yeah, you can deal with that, like depending on the different type of loss, you can deal with it afterwards. But computing the derivative would almost always be a vector.
Yeah. Okay. And then you combine it all into like the final loss, like which is one number. Essentially, the aggregate, whatever. I see. Thanks.
Yeah, I don't think there's an example, at least that I know of, where the loss would be a two-dimensional vector or like a matrix.
Yeah.
Are there any examples of functions which we didn't cover for which calculating a derivative is much harder? These rules are not applicable.
Could you repeat the question again?
Yeah, the question is, are there any examples of functions for which like calculating the derivatives would be much harder and these rules won't be directly applicable?
I'm sure there must be, but for the most part, we covered all the bases, right? Whenever the function is a sum of two different, when the loss is a sum of two different parts, or the loss is a product of two different parts, and this is almost always going to be the case. So even if there's a more complex function, like I said before, you can always apply the chain rule, break it down into different parts. And when you, like at the most fundamental level, when you apply one of these ways of computing the derivative, you should be able to get your answer. All right. Any other questions? All right, for you.
Okay, cool. So for now, we have already got some ideas on how to calculate the derivative for some simple operations. So it's time to move on to some complex functions with a lot of moving parts. So the key point here is that no matter how complicated a function is, we can always split it up into some smaller parts with the help of intermediate values. So with the help of intermediate values and with the help of chain rules, we can easily get the derivatives backward for a complex function. And since we want to make the operation as easy as possible, for here we only consider the unary or binary relationships between the input and outputs. For unary relationship, we talk about the case that we only have one input from the function. For say sigmoid and tangent h, we only pass through one input and get the output. And for binary relationship, we combine the two inputs to get an output. For say we can add up the x and y to get z, or multiply the two parts together to get the z. And this can be definitely generalized to the matrices. And yeah, let's move on to a more complicated example and see how the intermediate values can help us during the calculation of the derivatives. Yeah, so suppose we have the input x1 and x2, and we would like to apply a bunch of find operations and let us through the activation functions based on the influence diagram shown above to get the output z1. And as we can see, the formula to do this operation is pretty complicated. It may look trivial to you guys because it's simply the forward pass for the neural network, but it's somehow hard to get the derivatives through it. So here we first want to rewrite the formula with the help of intermediate values. So the first step is to write out the wx1 times x1 into a terms called I1, and we do similar things to the multiplication between the weighted matrix x2 and the input x2. And for x3, we consider everything inside the tangent h, so it should be a simple submission between the I1, bx1, I2, and bx2. And we simply pass this I3 into the tangent function, and we can get the y2. And we do similar things to another pass where we multiply the weighted matrix with y1 and wy2 to y2 to get the I4 and I5, and take the summation over the I4, by1, I5, and by2 to get the I6. And eventually we pass this I6 through the tangent h to get the output. So you might be familiar with all those operations because it's basically the forward pass, but here we want to write it into the terms of intermediate values. And let's keep moving backward and see how those intermediate values can help us when we calculate the derivatives. So basically it splits up the derivatives into, it split up the forward pass into some simple operations, and with the help of chain rule, we can get the derivatives of loss with respect to each intermediate values. And since those intermediate values are combined with simple operations, we can apply what we have learned before, those differentiation of the simple operations to get the derivatives of the loss with respect to every term we want at the end of the day. So for now, suppose we already have the derivative of loss with respect to the output z1. Let's gradually moving backward. So the first step is to calculate the derivative of loss with respect to I6, which is the final step. We want to calculate the derivative with respect to the final step before the activation function. And here we apply the chain rule. And as you can see, the only part we need to calculate is the derivative of z1 with respect to I6. And this is basically the derivative of tangent h function. And it is 1 minus tangent h squared. And let's keep moving backward. Since the I6 represent all parts that combines to the input of tangent h, it's basically the summation of the I4, by1, I5, and by2. And since we only add up each part for once, so all the derivative of loss with respect to these four terms are simply the same with the derivative of loss with respect to I6. Oh, wait a sec. I think, sorry, can everyone hear me now? I'm asking the Zoom guys.
Yes, we hear you clearly.
Okay, cool. I just saw some chats saying that the mic is mute. Okay, cool. Let's keep moving backward. Okay, cool. And moving backward, we want to calculate the, since we already got the derivative of loss with respect to I4 and I5, and let's take a recap on the term of I5. It is the multiplication between the WY2 and Y2 itself. So here we want to incorporate what we learned previously. So this is the matrix vector multiplication. And let's recap on how to take the derivative of this one. So since we want to get the derivative of loss with respect to the weighted matrix, we have to multiply the vector, which is the y2 on the left-hand side. So as you can see, this is basically the outer product between y2 and the derivatives. And later on, if we want to get the derivative of loss with respect to y2, we simply multiply the matrix on the right-hand side to make sure the shape is correct. And we do similar things to I4, and I won't go into details in this part because it is basically the same. And for now, we already got the derivative of loss with respect to y1 and the derivative of loss with respect to y2, and we can keep moving backward with the help of all these intermediate value i's, and the process should be the same. We first calculate the derivative of loss with respect to I3 and keep moving backward. Since it's basically summation, we directly took the derivatives and calculate the derivatives for matrix vector multiplication, and eventually got what we want. What we want is the derivative of the loss with respect to W, with respect to bias, and maybe with respect to the input X. Any questions so far? Okay, cool. Seems like we're good. And we're moving to the last part of this recitation. This looks trivial, but it is actually important when you try to coding your forward and backward paths. You want to know when to use equals and when to use plus equals. So basically, every time we calculate the derivatives, it is hard to tell if we want to add it up to the original value, or do we want to directly set it to the values as the derivatives. So here we can follow several rules to figure out when to use equals and when to use plus equals. So during backward computations, when the first time the derivative is computed for the variable, we should use the equals. We should directly set it to the set the value computed to the derivatives. And when we found there are multiple paths from the variable to the output, you have to use the plus equals to add up the derivative you computed from the different paths through back to the variable. And here's a cheap trick to do this thing. You can initialize all derivatives to zeros and simply use the plus equals every time you calculate the derivatives and aggregate it up. And can somebody tell me in those two figures, which one should we use plus equals to calculate, to aggregate the derivatives? Sorry? If you are using the cheap trick, you can use both. But if we only focus on the times of the contribution from the input to outputs, for which one we should use plus equals. Right. Yeah, exactly, because we have two paths from x1 to z1. The first one is x1, y1, z1, and the second one is x1, y2, z1. And yeah, this is basically what we have for today. And there are multiple references, like the recitation slides for past years. And we also have posted a Piazza post. You can check it out. And there's a reading materials attached. It can help you to better understand the derivatives, the shapes, and the influence diagram. Please do check it out. Any questions? Feel free to drop Zoom and leave if you have no question.
Thank you.
Thank you. Go ahead. Yeah. In the input data section, and for each item, it's just and make you can slide your context.
I just can't think of anything. Okay, so the first one is the makes sense, right? You're loading it again. And then after that, the document is just loading.